one other free body diagram situation. People wanted more about inclined planes, and we already did an inclined plane situation. Remember, we had the mass, and we found that the acceleration is, the inclined angle is theta, mass m, and we said that the acceleration is g sine theta. Okay? We will do a slightly similar situation for which we have a demonstration. We have a pulley, and we attach a string to this pulley, and we hang a mass m. This is called m1. Let's call that m1. We'll call the hanging mass m2. Just like we have here. See that? Right here. And the acceleration of this thing is 0. Right? Question is, for example, how much mass is hanging here? How much mass do I need to hang in order to have 0 acceleration? Let me say something about pulleys and what they do. For the time being, there is tension in the string. This string is pulling up in that direction. Pulleys change the direction of the tension without changing the magnitude. In other words, whatever tension I have here, I will have here. The same thing. But the direction changes. The magnitude remains the same. Okay? So now, if I look at this thing and I ask myself the question, in this part of the string, what is the magnitude of the tension? Is it greater than the weight, equal to the weight, or less than the weight? What do you think?
Less.
How many people say less than the weight? How many people say equal to the weight? How many people say greater than the weight? Well, forget that this thing exists. Suppose I hold it with my hand. Then whatever tension is in here is over there. This thing is at rest. And we said whenever a hanging weight is at rest or moving at constant velocity, only then we can say that the tension is equal to the weight. So this is one of those cases where we can safely say that the tension is equal to the weight. Okay? Not the weight of the cart, hanging mass. Now let's see how this hanging mass is related to the weight of the cart. We draw a free body diagram of this thing. We have our system. We have one force this way. We have the earth mg down, m1g down, and we have the normal force and up this way. Okay? We have three things now. We have an earth, we have a spring, and we have an incline. Three things, three forces. As before, remember we said last time that the angle between gravity and the direction perpendicular to the incline, that's the angle of the incline theta. The component of the weight in the y direction is m1g cosine theta. The component of the weight in this direction, this is all stuff that we've done before, so I'm not going to show you how it's done. Look in your notes. This one will be m1g sine theta in that direction. And now that I have drawn the components of the weight, I can take the weight out. I started with 3 arrows. It looks like I have 4 arrows, but I don't really have 4 arrows. I have 3 arrows. I broke one into components, x and y. Okay. Now I see that these two should give me 0 when added, because the net force is 0. This thing is not accelerating. These two should also give me 0, because it's not accelerating in the x direction, it's not accelerating in the y direction. Both components of the net force are 0. And what I get then is a relation between the tension and the component of the weight along the direction of the incline, namely T minus M1G sine theta is equal to 0. That's from this free body diagram. And from the hanging weight free body diagram, I have another equation, namely T minus M2G. M2 is the hanging mass now, is also equal to 0. This illustrates the use of two free body diagrams to find the answers. So now I can put these two together, and I say to myself, well, this tells me that this and that must be equal, namely M1G sine theta is equal to M2G. Therefore, the mass of the cart, if that's what I'm looking for, M1 is equal to, the G's will cancel. M1 is equal to M2 divided by sine theta. Okay? Any questions? Now we're going to do something else. Turn the screw one turn. And that is hang a weight and the weight is hanging in a direction perpendicular to the incline. Okay. It's about 50 grams worth of weight. 50 grams worth of weight, which means what? Now, if I look at the pieces of the universe acting on this object, let's write them down here. They still are the same. I have Earth, I have incline, I have string 1 and string 2. Before I only had string 1, now I added an extra string. This is string 1, that's string 2. Okay? Is this thing still in equilibrium? Acceleration still 0? Okay. What have I changed? What have I changed? I added some more force in that direction. So why isn't this thing accelerating if I added this force?
Not enough.
Not enough? What does that mean?
More force.
Before, look, before, okay, it doesn't move. I put a force perpendicular to here, and it still doesn't move. So, how come? Something must have changed. In addition to adding the weight here, yes?
I was going to say that.
Never mind. Okay. Anybody else have some ideas? Yeah. The normal force changed. These are contact forces, remember, and they adjust themselves to produce the observed acceleration. So the more weight I put here, the lesser the normal force is going to be, so that the sum is going to be equal to whatever it was before. Namely, in this case, the sum is going to be M1G cosine theta. Okay? So let's keep putting on masses and see what happens. Put a big one. Put another big one. The normal force is still being reduced while the tension increases. Okay? Put in some more. And some more. And even some more. So let's imagine now what's happening. Let's imagine what's happening. In this direction, I have N and I have T2, where T2 is the tension in string T. And the sum of these two is M1G cosine theta. Okay? The more T2 I put in, the less N I have, right? Okay, suppose I have enough T2 then, that is enough mass here, so that this weight here is m1g cosine theta. What should n be then? 0. N should be 0. What does n equal 0 mean? The incline is not there. That's a piece of the universe that no longer interacts with the system, right? Right? You believe that? There's one way to show that. Just remove the incline. Get that? Okay? I can put this piece of the universe in or take it away, and nothing changes. Now, if we look at this, and what you see is two masses, or two strings, basically, and a hanging weight. What you should see is vectors adding up to give you 0. Vectors adding up to give you 0. What are these vectors? These vectors are tension T2, tension T1, and the weight mg down. Right? Which I would draw this way, will be up the incline, will be T1. In a perpendicular direction will be T2. This is a right angle, and this would be m1g down. Okay. How do we add vectors? Remember, they're like displacements, if you will. Walking from, you start here, you go there, and if I want to add T2 to this vector, what do I need to do? I need to go parallel to itself, up there, by an amount T2, right? That's how we add vectors. And then, go down in the same direction as the third vector. And this is another diagram of the same thing. It has to be a closed triangle because the sum of these vectors is 0. I start here, I go by an amount T1, I add a T1 that is, I go by an amount T2, I add T2, I go by an amount mg down, I add mg down, and I end up where I started from. That is 0. Okay. And now you can see quite easily the relation between the tensions and the weight mg. This is not the right angle anymore. This is a right angle. The two forces are at right angle. This is a right angle. What's the relation? What's the relation? It's a relation that was discovered 3,500 years ago. What's the relation?
A squared plus B squared.
Not 35, maybe 3,000. It's called the Pythagorean theorem. The Pythagorean theorem. M1g is equal to the square root of T1 squared plus T2 squared. And if I have 4 vectors, same thing applies. Vector A, vector B, vector C. If they add up to 0, vector B. They form a closed 4-sided shape, and so on, for as many sides as you care to have. Any questions? Okay. Now, we will do a problem with rotation and centripetal acceleration. Here is a tray. Yeah, you can take that away, Dave. Thanks. Let's thank Dave for his help. Okay. Interestingly, let's draw a free body diagram. More interestingly, there is water in here. Is there water?
It's crazy.
I can put some more. And I can put this here and do the same thing. You think the cup will fall?
No, it won't fall.
Okay. There goes nothing. So, what's going on here? More interestingly, let's draw a free body diagram of this cup. To pour the water out. This cup is of water. Pretend there's water in here. I will draw two free body diagrams. I will draw, first of all, a free body diagram on the cup is at the bottom of the trajectory. And this is the center of the circle. Okay? And this is along the vertical direction. Now I need a system. I am questioning why the water doesn't fall. So I'll pick as my system the water. Just the water, nothing else. Just the water. You can pick anything you want. So here is the water in the shape of the cup. And as before, I need to list all the pieces of the universe that act on this system. And what do we have? We have an Earth. What else do we have?
Tray.
We have what?
Tray.
The tray.
Normal course.
You took it away. Is the water in contact with the tray? No. Forget the tray. The tray is not the cup. The cup, not the tray. If my system were the cup and the water, then I would say tray. But now it is not. So I will say earth and cup. What else?
That's it.
That's it. Earth and cup, that's it. The next thing we need to do is draw arrows, one arrow for each object. So here is the weight of the water mg straight down, and I need another arrow for the cup. In what direction do you think the cup force is? Straight up. Cups push up on the water, they don't pull in. Okay. It's like a normal force, if you will. All right. So let's call this F sub c. And now I have exhausted all the arrows. I enclose my diagram in a dotted line. And I want to declare the acceleration. Declare the acceleration. What is the acceleration? In what direction is it? Straight up. Towards the center of the circle. It's the centripetal acceleration. Straight up. And let's put down how big it is. V squared over r. Okay? What am I asking myself? I'm asking myself to find the force that the cup exerts on the water. Okay? Apply Newton's second law. We need first to find the left side of Newton's second law. The left side is the net force. How do I get the net force? I look inside my diagram. Whatever is up is positive, whatever is down is negative. Okay? So the net force is F sub c minus mg. That's the net force. And I need to set that equal to mass times acceleration. Okay? Here's the mass. Now, that's why I drew the arrow up. I drew the arrow up to remind myself that it's positive. It's up. Times v squared over r. And if I want to solve for the force exerted by the cup, that will be equal to mg plus mv squared over r. Okay? No big deal. That is the force exerted by the cup on the water. Now let's do the same thing, except that we put the water up there at the top of the trajectory. No, yeah, it's at the top of the trajectory. I will draw it here so you can see what's going on. The pieces of the universe are still Earth and cup. That hasn't changed. Draw an arrow for each one of these. In what direction is the Earth force? That's the easy one. That's straight down. mg. In what direction is the cup force? Straight down also. F sub c. In what direction is the acceleration? Straight down. Take that away. It's still v squared over r, but now it points straight down. That's how I modify the diagram for this other situation. Okay. The left side is, now I have two down arrows. That changes because I have two down arrows. That is, I need to put a minus sign in front of FC also. Another thing that changed is the acceleration. I need to put a minus sign there. So I have three minus signs. And because minus signs confuse me, I can change them all to plus signs by multiplying both sides of the equation by -1. And now I solve this equation by moving mg over to the other side and changing sign, and I get m. I will factor out m so you can see better what's going on. Inside I have v squared over r minus g. Now, as long as v squared over r is greater than g, I have a normal force, and the water is held in the cup. What if I don't spin it fast enough? That is, you remember now, the less v I have, the slower I move this thing, the closer f sub c is going to be to 0. What happens when f sub c is equal to 0? That is, I spin this so that this thing here, this term, is 0. The water will fall and I'll get drenched. So the idea is to spin this thing fast enough so that you don't get drenched. Okay?